Well, welcome. This is Dr. Morton, and this is class day 12, and I'm going to start chapter 6. The first exam was completed on Friday, and the average was just a little over 60, which I was a little disappointed with. And so what I would say is I think I'll have class. Maybe not next week on Wednesday, but the week after, or maybe I will do it next week. I'll let you know. I'll let you know. Yeah, I think what I'll do this Wednesday, so that'll be, today's the 19th, so that'll be the 21st. We'll go ahead and have our afternoon class in the engineering building up on the 3rd floor where we did before, and we'll meet. I think it's 2, right? I'll double check that. Yeah, so it's in engineering building, 3rd floor. So it's 30430 is the room number. It's where we met before, and it is at 2 o'clock. And we'll do that this week, Wednesday. What I want. What I'll do, I'll give everybody a chance who did poorly on the test to we'll go over the test, we'll do some corrections, and we'll give some points back. So I'd like everybody to show up on Wednesday, and especially if you didn't do well on the test, and this will be your one chance to get some points back. So be sure and be there this Wednesday. Okay, the 21st. All right. So let's look at the syllabus real quick. So here's the syllabus, and we're on the 19th. One of the things, so we're going to start chapter 6, K-maps, and what I want you to also do is I want you to group up in project teams. So need to email and talk to your classmates and see if you can form up in groups of 4 or 5 students, and then pick one person from the group and have them send me a list by email of all the names of everybody in the group. And then what I'll do is I'll assign you a group number, and I'll basically that'll allow me to get things set up. We'll do a group project, and the group project is going to involve a combination of design for driving a 16-segment alphanumeric display, and you'll be assigned probably 6 letters or symbols or numbers or some mix thereof to display, and you'll have a 3-bit variable that will give you that'll represent the 1 through 6 numbers you have to display, and then there'll be some don't cares, and you have to do the design, and then you have to put it in a logic simulator like Simuade, and then actually simulate it. And you'll need to do some PowerPoints, and I'll give you all the details about what you have to do. But first, you need to form up into groups. And there should be, we only have 22, I think, in this class. So really, 4 groups of 4 groups of 5 would be 20. So I would allow maybe a couple of groups of 6, possibly, or groups of 4. So 4, 5, or 6. And so go ahead and try and get in groups, and then pick one person, send me a list. And I want everybody to try and do that this week, be in a group. Okay. And then there is a chapter 6 video that goes over K-maps, and you should look at this. So let's see. Let me do this. Let's see. We've got. Okay, so here's our book, and if you scroll down, here's the video, and it kind of goes over the whole book. So you should definitely look at this, and then I'm just going to do I'm going to talk a little bit more specifically about K-maps right now. Okay, so I think I'm going to use the slides for that. Oh, before I do that, I did want to mention, homework. So there is the next homework 6 is due on the 28th. So that's next week. So be sure you're looking to that. And then this Saturday you have the end of chapter 6 quiz. Note that on October 1st, which is a week from this Saturday, you have chapter 7 and 8 quizzes to do. So make sure you don't mess up and only do one quiz on October the 1st. But you've got a little bit of time before we get there. Okay. So I'm going to go through some slides first here. So K-maps basically have some really great uses. This is kind of my second favorite lecture because, we'll just kind of get into K-maps. I'm not going to fully flesh it out. I just want to get started today. But so we can use them for functions that have 2 to 6 variables. It's hard for 6, but for 2 to 5 it works pretty well. And they take advantage of some of the natural human visual system abilities that you have. And so that's one of the reasons why students really like them, because it makes things visual and obvious, and it actually makes simplifying logic expressions really pretty easy. And the only limit is that once you get past 5 variables, 6 variables at the most, it becomes it's not usable. You can't really use it. All right. You can represent. You can have a function, and you can plot it on a K-map, and then turn that into a truth table. You can simplify a logic expression with it. That's really its primary purpose. You can convert from SOP to POS and POS to SOP. You can find all the terms in a logic expression, and you can take a logic expression and plot the terms in a K-map, and see all the min terms. And you can prove logic equations. You can do 2 K-maps and plot your expressions, your left side on one K-map and your right side another, and they should be identical. And then and there's some other uses too. So they really are great tools, and we use them extensively not only in combinational design but also in sequential design. Now, remember I said at the beginning that this course has three main parts, and remember that we've now finished part 1, which was a Boolean algebra, codes, binary math, and the canonical forms of SOP and POS that we get from a state table. From a truth table using a min term or a max term expression, and then algebraic manipulation, conversion from SOP to POS and POS to SOP, and also simplification using switching algebra. So we've really covered those things and tested you on them. And now we're into the second part of the course. The second part of the course is where we're going to talk about, really focus on combinational design. And we're going to talk about how you can share terms between 2 output functions. We're going to talk about how you can use K-maps as a tool. Sorry, I had to sneeze there. And I was able to pause it just in time. Anyway, so we're going to do a bunch of stuff in this part of the course. And then the last third of the course is going to be sequential design. And we're going to use a lot of combinational design in our sequential designs. So all the things you've learned are cumulative, and you're going to be using all of the stuff at the end of the course. Okay, so this is the beginning of the 5th week. So when we finish this week, we will be 1/3 of the way through the entire course, and actually maybe a little more than that, because I think we maybe only have 14 weeks, and then the 15th week is finals week. So the course, so the semester is going fast. So if you're behind, be sure and come on Wednesday, and we'll see if we can't get everybody caught up so you understand everything we've covered up till now. All right, K-maps. So these are called Carnot maps because some other things. We're going to talk about how we can use this to get the minimum form of switching function. And we're first going to start with 2 variable and 3 variable K-maps, and then we'll do 4 variable K-maps. I'm going to talk about consensus terms and prime implicants. And under prime implicants, I'm going to talk about essential prime implicants and non-essential prime implicants, which basically turn into be consensus terms. There really are consensus terms for the most part. And then we'll touch on 5 and 6 variable K-maps. They're kind of the 6 variables especially are awkward. The 5 variable are workable. And we'll talk about alternate labels, and then yes, and how you can use them for factoring and simplification. All right. So we've talked about this before, the minimum form of a switching function. We talk about the cost of a switching function. And remember, it's directly related to the number of gates, and then the total number of inputs to all the gates, and then layers. Now, layers doesn't impact cost so much as it does the propagation delay through the network. And when you add a layer, you add an additional propagation delay because you're adding additional gates. So it has to go through not 2 gates to get through the network, but now potentially 3 gates. So that's an additional propagation delay. And then remember the minimum form of either the SOP or the POS for that matter is the function that gives all the correct values for f for all the independent variables, for all the combinations of the independent variables, but has the least terms and the least number of literals, and obviously is 2 layers. Okay, now in many cases the minimum form is not unique. There may be several minimum forms that are equivalent but different, and you'll see that. And this happens all the time. Sometimes it is unique, and sometimes there's 2, and sometimes there's 3 and 4, so it varies. The simplification theorem that is tightly wedded to K-maps is this theorem here: xy prime plus xy equals x, and then the corollary x plus y prime quantity times x plus y equals x. This is how K-maps work. We set them up so every box in a K-map differs from any box that's connected horizontally or connected touching vertically, only differs by a single variable, and we can apply this theorem and combine those boxes if they're both desired minterms and drop one of the variables. And then maybe we can take 2 boxes and combine them with 2 more boxes to make a group of 4 boxes and drop another variable. Or maybe we can take the group of 4 with another group of 4 and drop another variable. Now, of course, it depends on how many variables the map is. In a 2-variable map, you can only drop 2 variables, and then you get to a constant 1, or maybe a constant 0 if you're doing max terms. So we'll look at this. So when we use switching algebra to simplify an expression, we have a little problem. So notice I have this expression up here, and I copied it down here, same expression. Here I combine these 2 terms, these 2 terms, these 2 terms, and these 2, and I get these 4 variables, these 4 2-variable terms, which looks like a nice reduction from this one. But it turns out I could have done it this way, and I would have gotten 3 2-variable terms. Well, when I did it this way, I didn't necessarily know that this was going to work out to be 4 terms, but I could have gotten 3 terms if I'd done it a different way. So when you do switching algebra, you're always a little unsure if you've got the minimum solution. There's no way to, there's no direct way to guarantee that in every case. But with a K-map, you can look at it and you can see, yep, I see the simplest solution. Your eyes actually help you to do that. All right. So and again, this is what we're going to use. Theorem S1. Here's the dual, the SOP, the POS version. Here's the SOP version. Okay. So let's take a 2-variable K-map. Okay, so we have here a 2-variable K-map, and so we put A across the top and B down the side. Now, just as a matter of convention, to help you learn this as quickly as possible and avoid confusion, I'm going to always use the variables A, B, C, D if we have 4 variables, A, B, C, D, E if we have 5. And then I'm going to call my functions, usually starting with F, depending. So in this case, we have a 2-variable truth table and the output F. Now, where do we get the F from? We get it from God or from our customer. Okay, it's given to us. And in this case, f is desired to be 1 for row 0, 1 for row 1, 0 for row 2, and 0 for row 3. And those correspond to these 4 boxes over here in our K-map. So we have A across the top, so 2 columns. We have B down the side, 2 rows. The top row, B is 0, and the bottom row, B is 1. The first column, A is 0, and the second column, A is 1. So for instance, in this box here, A is 0 and B is 0. That corresponds to the first row. Down here, A is 0, B is 1. That corresponds to the next row, row 1. Here, A is 1 and B is 0. That corresponds to row 2. And finally, we have A is 1, B is 1. That's row 3. Because F is only 1 at row 0 and 1, we put a 1 and a 0 over here. So I'll do that. Let's see, I don't think yeah, we put those in right there. And let's see, I think I can do pin. Yeah. So we could put a 1 here and a 1 here, and we're going to put a 0 here and a 0 here. Now the way this works, if we're doing the min terms, we're going to see if we can group the ones. We can only group in powers of 2, which would be a single box all by itself, 1, 2 boxes together, a group of 4 boxes, a group of 8 boxes, or 16, and so on. Powers of 2, only powers of 2. You can never group 3 boxes or 5 or 6 or 10. Only 1, 2, 4, 8, 16, 32, and 64, and so forth. In this case, since we only have 4 boxes, the most we could group would be 4. And that would give us, if there were 1s in all 4 boxes, that would be the constant 1. We would drop 2 variables, have no variables left in our solution. It would just be F equals 1. Or we would tie F to our voltage. Say it's 5 volts, F would equal 5 volts. All right. And if all the boxes were zeros, then we'd have the constant 0, and it would be F equals ground, or false. All right. Okay, so here we are, and for some reason I can't see my pointer. Yeah. Oh, I see. It's because I'm writing with it. All right. So what I'm going to do is erase all the. Okay. So, oh, well, one thing I did want to show. Okay, put my 1s back. So I put 1s. A lot of times, if I'm looking for the min terms, I don't put in the 0s. If I'm looking for the max terms, I don't put in the 1s. I just put the 0s. But in both cases, if I have a don't care, I'll put the X's in, because we do want to include the don't cares potentially in the midterms and potentially in the max terms. All right, so since I have a 1 in this box and a 1 in this box, I can loop these two like this with a little loop. And that means I'm joining these 2 boxes together. I'm going to drop 1 variable. So what variable drops? Well, in this box, A is 0 and B is 0. In this box, A is 0, B is 1. So the B changes. Now, if you go back and look at this law, notice here we have x, y, and here we have x, y prime. So the y changes in these terms. And I drop the y and I just get x. Okay? Now I'm going to erase the ink. Okay. And then we go back here. And so now that I've grouped these boxes, what I do now is I read off what this group of 2 is. Well, if I drop the B term, what am I left with? Well, remember in this case, A is 0. So we would call this box A prime B prime. We would call this box A prime B. Since the B changes, we drop it, and we're left with A prime. And you can see this. This whole column is A equals 0, or this whole column is A prime, and this whole column is A equals 1, or A. This top row is all B prime, and the bottom row is B, because B equals 1 here, and B equals 0 for up these 2 boxes up here. All right. So the answer then is A prime. And that's this group of 2 right here, these 2 boxes. All right, let me erase this ink and we'll press on. Okay. And I think I can go back to this. Okay. All right. Now we, okay, now, again, that's how we do that. Okay, so here's what it looks like. We group these two boxes. We read off A prime. So the answer is F equals A prime. And we know that because it's A prime B prime plus A prime B. We combine these and we just get A prime. Okay, like that. Okay, and then if we write out the min-term expression, it's xy prime plus xy equals x. Well, that's the theorem. Here's the min-term expression. And then it reduces to F equals A prime. All right, let's look at a three-variable map. Now, for three-variable maps, we have a little wrinkle. We're going to have to flip the bottom two rows to still be able to use our theorem. So let me explain. And for that, I think I'm going to switch over to writing on the paper. So let me do that. And hopefully, let's see if I got. Yeah, I think that's good. Okay. So let's do this. So let's do a little K-map. In this case, I'm going to do a three-variable map. So my variables are going to be A, B, C. Remember I said I'm always going to use A, B, C, D because it'll just help you a lot. Now, you know, that's just a decision that's kind of arbitrary. Obviously, any variables could be used, but it's going to make it easier for you to learn K-maps. And then once you get comfortable, you can use whatever variables you want. I still use ABC for everything, and even if I'm using like W, X, Y, I'll just do it in ABC, and then I'll let A be W and B be X and C be Y, and then I'll just change it over once I get my solution because I make less mistakes if I use ABC. But whatever. Sometimes I'll just do it directly. But I'm going to try and use ABC. And when I do a three-variable map, I'm always going to. We have two different ways we can do three-variable maps. We can do a single row and 4 columns. Well, 2 rows and 4 columns, or we can do 2 columns and 4 rows. I'm always going to do the 2 column 4 row approach instead of the 2 rows 4 columns. So 4 rows 2 columns versus 2 rows 4 columns. And I'm always going to put A at the top and BC down the side. Now this column will be A equals 0, and this column will be A equals 1. This is B and C are 0, 0. This is 0, 1. Now, if I were going straight binary, this would be 1, 0, but I'm not going to do that, and this last one would be 1, 1. I'm going to flip those around. I'm going to put 1, 1 here and 1, 0 there. And the reason I'm going to do that is because I want every box to differ from its neighbor vertically and horizontally by only a single variable. And if I don't flip these bottom 2 rows so that I'm basically reversing the binary order here and I'm doing it out of binary order, if I don't do that, then what happens is I can't use that theorem for the bottom 2 rows. Well, that's terrible. I want to use it for all the rows and all the columns. So I'm going to flip these rows. Now when we go to a 4-variable map and we have 2 more columns over here, then I'm going to also flip these columns. These columns are going to be flipped too. And my A is going to be, then I'll change it around, and I'm going to have A and B on the top, and I'm going to have C and D on the going down. And my A and B will be 0, 0, 0, 1, 1, 1, and 1, 0. And what that does, that means that every single column as I go this direction or this direction only differs by a single variable, including my wraparound column. The 1, 0 only differs from 0, 0 by a single variable, the 1. This only differs by 1, the 1 changed to a 0, and here we have 0, 1, so the 0 changes to a 1, and here we only differ by 1, the 0, 0 changed to 0, 1. Same going down. So when I set it up this way, flipping the bottom 2 rows and the rightmost 2 columns, I wind up with a map that allows me to use that theorem on any boxes connected horizontally or vertically. And again, that theorem is x y prime plus x y equals x, or x plus y prime quantity times x plus y equals x. So this is the POS version, and this is just the SOP. So with this I'm using the zeros, with this I'm using the ones. Okay? All right. So let's go back to my 3 variable map. Again, I'm going to do it vertically like this. I'm going to put A at the top. A equals 0 and equals 1. And then I'm going to do B and C down the side. And that'll be my 3 variables, A, B, C. B and C down the side. 0, 0, 0, 1, 1, 1, and 1, 0. Again, I flip these bottom 2 rows. Now, if I number these boxes to correspond to a truth table, so let's do my truth table. So here's my truth table. We have A, B, C, and here's my F. So we go 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and finally 0, 1, 0, 1, 0, 1, 0, 1. So, and my F, say, I'll just put in some numbers, doesn't really matter. Okay? So I number these, all rows in these truth tables are numbered. Remember, we start with row 0, then row 1, 2, 3, 4, 5, 6, and 7, which actually corresponds to the binary values of our ABCs. 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, and so forth, and 1, 1, 1 is 7. So you can just look at this and get the number. I can number the boxes just by writing over here, 0, 1, but remember, box 2 is not here. Box 2 is actually down there because I reversed the order. Then there's box 3, then box 4, 5, 6, and 7. So when I copy these over, I make sure I get them in the right box. So 1 goes here, because that's box 0. 1 goes here, because that's box 1. 0 goes in 2, so I'll put a 0 down there. And then a 1 goes in 3, and then a 0 in 4, and a 1 in 5, a 1 in 6 down here, and a 0 in 7. So that's my final K-map. I have some 1s and 0s. Now when I group them, here's how I would group them. I can only do, I can't do a group of 3, right? That's not a power of 2. So I can group these 2. I can group these 2. I can group these 2. Now, can I group this one with any of those? Is it connected horizontally or vertically to any of these, or even using wraparound? No, it is not. It's all by itself, so I take it as a group of itself. So this one is going to be a 3 variable term. These are groups of 2, so they're going to drop 1 variable. So they're going to be, we have 3 variables ABC, now we just have 2, so it's going to be a 2 variable term. And all these are going to be 2 variable terms. This group, and that group. Now, how do I read these off? This is what takes a little bit of practice. You do have to work on this, and it does take a little bit of practice. So you really do have to work on this. And the more you do it, pretty soon you'll just be able to look at these. But let's try this. I'm going to write this a little bigger. I'll write the same one, and I'm also going to delete the zeros because we don't need the zeros. Yeah. So this is good. So again, I'm always going to draw my 3 variable maps, 4 rows and 2 columns. I'm going to put A on the top and BC down the side. Now later on, when we do sequential designs, we'll have an X up here and we'll do some of that. But right now, we're just going to do A, BC down the side for 3 variables. For 4 variables, I'm going to do AB across the top and CD down the side. All right. Now the way I think about this, I think about this whole row is A, and so I'll write this alternative label up here, A. But then this whole row, this whole column is A, this whole column is A prime. And then with the B, I know that the top 2 rows are B prime, and the bottom 2 rows are B. So I'm going to write down here B, and then the middle 2 rows are C, and the top and bottom rows are C prime. The top 2 rows are B prime, the bottom 2 rows are B, the top and bottom rows are C prime, and the middle 2 rows are C. So let me put in the numbers and you'll see how this works. So I have 1, 1, 1. I'm not going to write the zeros in because it just clutters up things. But if I had don't cares, I always would include them. So I have 3 groups, and then I have a 1 down here all by itself. Now this one, we can write to begin with. So that is going to be, this is in the A column. It's also in one of the B rows, but it's not in one of the C rows, so it has to be C prime. So this is going to be A, B, C prime. Because remember, the bottom and top rows are C prime. Now, this group of 2, it's going to be A prime, because A is prime for this whole column. So for this group of 2, it's going to be A prime. We know the top 2 rows are B prime, but we know that the very top row is C prime, and this row is C. So C changes. So it's going to be, so this group of 2 is just going to be A prime, B prime. Now, this group of 2 right here, right there, that is still going to be A prime, because it's still in the A prime column, but it's not going to, B changes. Here, B is 0, here's B is 1, so we're going to drop the B, and the C is 1 for both these, because the middle 2 rows are C, right? C, so it's going to be A prime C. And then this group of 2, I already know A changes, because here A is 0 and here A is 1, and I know, if I look at my side, I know that this is, this up here is 0, 0, this is 0, 1, this is 1, 1, and this is 1, 0. So I know this is B prime C. So this group of 2 there is B prime C, and the A drops. So my final solution is F equals my 3 variable term, A, B, C prime, plus B prime C, plus A prime, B prime, this group of 2 here, and finally this group of 2 here, which is plus A prime C. So A, B, C prime, a 3 variable term, and then 3 2 variable terms, B prime C, A prime B, and A prime C. And this cannot be simplified any further. I know this because I can see I can't group these anymore. And therefore I know that I can't shrink this. This has got to be A, B, C prime. I know these are going to be 2 variable terms, and I have 3 of them. There they are. And I know that's my optimum solution. Done. So that's how that works for a 3 variable map. And then we'll pick up with 4 variable maps. We'll do 4 variable maps when we cover this on Wednesday. Okay, so I think I'm gonna leave it there. So what I would recommend you do is definitely do some practice on this, and I'm going to pick it up. I'm going to start talking about 4 variable maps. I'll also talk about how we do the max terms. But first, I'm going to talk about the min terms. There was one more thing I want to cover, and that's the concept of implicants and prime implicants. So, any group of any box by itself, any group of 2 boxes, 4 boxes, 8 boxes, whatever, those are all called implicants. If you can combine an implicant with another implicant to make a bigger group, twice the size, because remember it's always powers of 2, then it's not prime. But if you cannot combine it to make a bigger group, also still a power of 2, right? So if you have 1, you can combine 2 and get a group of 2. If you have a group of 2, you need another group of 2 to make a group of 4. If you have a group of 4, you need another group of 4 to make a group of 8. Now, the group of 8 would only be relevant if you have a, say, 4 variable problem, or maybe even a 5 variable problem. But because in a 3 variable map, you only have 8 boxes in the entire K-map. And so a group of 8 would be all 1s or all 0s, where you would have dropped all the variables and you just have a constant 0 or constant 1. So when you can't combine an implicant with another implicant, we call it prime. So prime implicants are as combined as they can be, which sometimes can be just a box all by itself, a single box, or it could be a group of 2, or a group of 4, or a group of 8, or 16, or 32, always powers of 2. Can't be a group of 10, or 7, or 6, or 3, just powers of 2. When you do your prime implicants, if there are 1s in your prime implicant that are not in any other prime implicant, then then that prime implicant is essential. On the other hand, if there are ones in your prime implicant that are covered by other prime implicants, and there's no ones that aren't covered by at least some other prime implicant, then in that case you have a non-essential prime implicant, which really is a consensus term. So let me show an example of that in this last K-map. We'll go back to this real quick, and then I'm gonna quit. So in this K-map, do you see any terms that have where there are ones that are not covered by any other term? Well, yeah. In this group of two, this one is not covered by any other. In this group of two, this one is not covered by any other. In this group of two, this one is not covered by any other. And this one all by itself is only covered by this one term and no other terms. So all these three two-variable terms and this one three-variable term are all prime implicants. And they're all essential. There are no non-essential. But if we had, say, another K-map, we'll just do a quick example. Say like this. Let's say we had two ones like this. And now we could cover these ones here, these ones here. Now we've covered all the ones in our problem. So that's sufficient. But there's also a group of two here that is a prime implicant, can't be combined with another group of two, but the ones in this group of two are both covered by other prime implicants. So this group of two is not really necessary, and it is a consensus term. And it is also non-essential prime implicant. Now these others are also they are prime implicants. They're all three prime implicants, but these two cover ones that don't show up anywhere else, so they're essential. If you don't include this prime implicant, then this one would never be in your solution, and it would be wrong. And same with this one. And it turns out you only need this one and this one to cover all the ones on the map, which is how you get a solution. You cover all the ones in the map with groups of either 1, 2, 4, 8, or 16, or whatever, depending on the map size. Remember, only powers of 2. Okay, so I think that's really what I wanted to cover. And I think with that, I'm going to stop. We're already at 37 minutes. I want to keep this short and also give you an opportunity to look at the video that's in the book. So with that, I think I am going to stop here, and we'll pick up. So I'll see you in class on Wednesday, and then I'll do another video for Friday. And we'll be well on our way to covering K-maps.